Hello, everybody. Let's talk about one of the most common problems that you're going to encounter uh, when you're working Newton's laws problems, and that's the block on an incline. So this question appears again and again. So it's one that you're going to want to know inside and out, and basically be able to come up with on your own. So the situation that I want you to consider is you have a block. And basically, we want to know how does it accelerate, and what is the normal force. And for this example, we're going to assume that it's frictionless, although we will work with adding friction to this later. But for now, I'll put here, for now, no friction. So, okay. The first thing that we would do when we approach this is put in the forces that we know. So the force of gravity will be down, the object's weight. The normal force, so I've tried to emphasize to you, the normal force is always perpendicular to the surface. That's what normal means. The normal force will be like this. Now, we're going to employ a strategy to help us solve this problem, and that is we are going to tilt our coordinate axis. Now, we're going to orient our coordinate axis along the plane, like this. And the reason that we do that is because this takes this problem where, notice, if this thing slides down and we had our coordinate system as we normally would, like this, it would be moving in both x and y at the same time. So instead, what we do is we tilt the coordinate system so that it's oriented along the incline, and this makes it so that it's only moving in one dimension at a time. It's only going to move in the x direction. And this simplifies the problem. Now, what this adds, though, or what this requires us to do, is we need to break this weight into x and y components according to this coordinate system. So in other words, we need to find this component and this component. So let me add a little more detail here. This is some angle theta. This block would have some mass. I'll just put m here. So we can think of this as, you could think of this as the force of gravity in the y direction and the force of gravity in the x. Recognize this angle theta would also appear here. This is also theta. Okay. So if we want the piece that is pointing along negative y, that is going to be mg cosine theta. Okay. And the piece that's along the incline, along x, this would be mg sine theta. Now, I want to emphasize that this is kind of tricky. So if you have just memorized associated cosine with x and sine with y, then this may give you problems. So I think one thing that you can use to keep track of this problem is to think about the limiting cases. So what I mean is, when theta goes to 0, let me actually draw it like this. When theta goes to 0, this thing would become basically flat, right? M's just sitting there. There should be no force that's going to push it in the x direction, right? mean, there's not going to be anything to push it along. So in other words, this has to go to 0 as well. And recognize that mg sine theta, when theta is 0, goes to 0. So that's what we want. Kind of by the same token, when theta goes to 90 degrees, so that's going to correspond to, actually this case. Think about like theta, when theta goes to 90 degrees. Now it's a little bit strange because our coordinate system is on the incline, right? So this would be x and this would be y. But now in this case, we would expect there to be a force, and in fact, we would expect it to be all of mg. So this is now just falling, in which case it would just be feeling its weight. So in this case, when theta goes to 90 degrees, this becomes just mg, as we expect. And we can do this sort of similar logic with the normal force. So if we're looking at the normal force, for the theta equals 0 case, the normal force better just become the weight. And that happens with cosine theta, because cosine theta, when theta is 0, would give us 1. And then by the same token, the normal force when theta goes to 90 degrees, when it's just falling sort of next to the ramp practically, there's no force, there's no component anymore that would be into the ramp anymore. So the normal force in this case would go to 0. So here we can just put it here. G cosine theta would go to mg, and that would equal the normal force, which was what we would expect if it's just resting on the table. And then in this situation, the mg cosine piece would go to 0, which is what you would expect. If it's falling, there's no longer a normal force between the block and the incline. So I present this in kind of a lot of detail just because I think this procedure is really helpful for keeping track of making sure to ourselves that the trig functions are making sense. So let's look now at the forces in x and y. So if we sum the forces in the x direction, what are we going to have? We have the component of the weight that is in x. And that's actually the only piece that's directed in the x direction. So this would equal m times a due to Newton's second law. So in other words, the acceleration, notice m is appearing here on both sides. The acceleration is just g sine theta. Okay. Now, this is describing how it would accelerate. And we should be careful. This would be in the I hat direction, so it's along the positive x direction. So that's the acceleration. And then if we look at some of the forces in the y direction, what do we have? Well, we have the normal force minus mg cosine theta, because it's pointed down, would equal the mass times the acceleration in the y direction. But there is no acceleration in the y direction because it's resting on that surface. So this would be 0. So this tells us that the normal force is equal to mg cosine theta. And of course, this would be pointing in the j hat direction. And it may seem right now that like this isn't that interesting, the normal force, okay, it depends on the angle. This will, being able to compute the normal force for different scenarios will be relevant when we talk about friction. So don't, don't kind of throw this out the window as being something that doesn't seem that important. It'll be helpful when we're working with friction in the next chapter. And I think that's oh, one other thing I would recommend is be sure that you can derive this on your own. This problem just appears so often that this is an important one to study. So let's look at a couple examples of making use of this. So paste an example or two in here. Here's a question for you. The block shown in the figure has a mass of 7 kilograms and lies on a fixed, smooth, frictionless plane tilted at an angle of 22 degrees to the horizontal. Determine the acceleration of the block as it slides down the plane. And if the block starts from rest 12 meters up the plane from its base, what will the block's speed be when it reaches the bottom of the incline? Okay, so we're going to re-put in our components just to practice with that. But let's add a little bit of information here. So it says that the block starts from rest 12 meters up the plane. So this indicates that this is 12 meters. Let's do a free body diagram. So we're going to have to break our, so the force of gravity is always pointing down. Normal force, perpendicular. And of course, now we have to remember to break this into the components in x and y. So the x piece here would be, this is theta. This would be mg sine theta. And this would be mg cosine theta. I would add here too, it helps if it's not clear that this angle is the same thing as this angle theta here. Imagine, oh here, let me draw it again. Like this. Imagine making theta really small. This would get flatter. And this angle, as I have drawn here, would pinch together as it gets small. I think that that can be a way to help visualize that that's the same angle. This angle and this angle are the same. But just a tip. In any case, now we have our x and y components. Let's do our Newton's laws expressions in x and y. So, and that'll help us to determine the acceleration. So we're not going to use it this time around, but the sum of the forces in y is the normal force minus mg cosine theta. This is going to equal the mass times the acceleration in y, but there is no acceleration. But just to practice here, this is telling us that the normal force is mg cosine theta. And then in the x direction, we're going to have mg sine theta equaling the mass times the acceleration in the x direction. Notice mass is appearing on both sides, so the acceleration is g sine theta. And this depends solely on the angle. Notice they give us a mass in the problem, but we actually don't need this piece of information to solve for the acceleration. So it's an extra piece of information. Sometimes questions will have that and it can distract you. You don't necessarily use everything in a problem to solve the problem. So let's put in our values here and come up with a numerical result. So the acceleration is going to equal 9.8 times sine of 22 degrees. Be sure to have straight if you're working in degrees or radians when you're evaluating your trig functions. And we would find that this is 3.67. So let's call it 3.7 meters per second squared. And this would be in the I hat direction. So notice our precision of the numbers that we've been given have 2 digits, so I'm reporting this number as a 2-digit number. I've rounded it to 2 digits. Okay, so that's part A. Part B, if the block starts from rest 12 meters up the plane, what will the block's speed be when it reaches the bottom of the incline? Well, this we can brush off our kinematics from chapter 2. And this is a good expression to use to solve this. So the final velocity will equal the initial velocity squared plus 2 times the acceleration times the distance. So it starts from rest, so this will be 0. We know the acceleration now from part A, so we can simply solve this for the final velocity. Take a square root of 2 times A times D. Put in our numbers here, 2 times 3.7 times 12. Notice when you actually compute this, I would use your unrounded value, but when we crunch the numbers, we find this is 9.4 meters per second. This would also be in the I hat direction, along the x-axis there. So there's the second part, using our kinematics, combining our inclined plane, block on an inclined plane, understanding with what we know about kinematics to solve for a velocity. Okay, let's look at another example. So this example, a block is given an initial speed of 4.5 meters per second up the 22-degree incline. How far up the plane will it go? In terms of height. So, and B, how much time elapses before it returns to its starting point? So, now, this is very similar, except we have an initial velocity. So, let's give ourselves a picture here. So this thing has some initial velocity, and it's going to go up and then come back down. So we're curious, how far up the plane it will go. So both like this, and also in terms of height. So how far up will it go? So to figure this out, we can use our kinematics expression again. Now notice the angle is the same as the question that we just looked at, so the acceleration will be the same. It only depends on the angle. So we can find how far up it's going to go by recognizing that's going to be where this velocity goes to 0. So it's going to get up to here, and it's going to stop for a moment. So we have an initial velocity. We know what the acceleration is. We can then just solve this for d. Negative E naught squared over 2a. Let's put our numbers in here. So this will be 4.5 squared, 2 times our 3.7. crunch the numbers, we find that this is 2.8 meters. Notice this is in I, but it's negative. And it's kind of strange, but that's a consequence of our coordinate system. Even though it's going up, according to our coordinate system, that is the negative x direction. So that would be negative I. Okay. Or negative I hat. So the other thing, it asks us, what is this in terms of height? So we could do a little trig exercise here. This is theta, and this is 2.8. Then we know that sine theta would be h over 2.8. So the height here would just give us 2.8 sine theta. And so this height is about 1 meter. Okay, and then, so that was part A. And then for the second part, how much time is going to elapse for this thing to go up and then come back down to where it started? So for this, we can make use of our other kinematics expression. Okay. So we can set our coordinate system such that x equals 0 at the starting point. So that means the initial height or initial position would be 0. This would also be 0. We recognize our initial velocity in this coordinate system is negative. So we could then solve this for the time. So one solution, would be time equals 0, but let's divide out a time equals 0, or divide out a factor of t, rather. 0 over t. So we have 0 equals v naught plus 1/2 at. And then we can solve this for t. This will be v naught factor of 2 divided by a equals t. Let's put in our numbers. 2 times 4.5 divided by our 3.7. This would give us a time of 2.5 seconds. So this is another nice example where we're connecting this new stuff, working with the block on an incline, back to kinematics. So you can expect problems like this in your homework and on exams, etc. So hopefully this helps give you some guidance on how you can approach problems like that.